Stars don't just fade away quietly into the night. They die in the most catastrophically violent explosions the universe has ever witnessed, and one of these cosmic detonations could reach across light years of space and obliterate all life on Earth in seconds. The question isn't if it will happen, but when, and which stellar death will be our executioner. Today, we're diving deep into every type of star death, from gentle planetary nebulae to reality-shattering hypernovas, and I'm going to tell you which ones pose the greatest threat to our existence. Let's start with the most peaceful way a star can die, because not all stellar deaths are apocalyptic. When stars like our sun reach the end of their lives, they don't explode. Instead, they go through a surprisingly elegant transformation. After spending billions of years fusing hydrogen into helium in their cores, stars like the sun eventually run out of hydrogen fuel. When this happens, the core contracts and heats up while the outer layers expand dramatically. The star becomes a red giant, swelling to hundreds of times its original size. In our sun's case, when it becomes a red giant in about 5 billion years, it will expand past Mercury's orbit, possibly past Venus, and might even engulf Earth. But this isn't technically a death yet, just old age. The real death comes when the star sheds its outer layers in gentle puffs of gas, creating what we call a planetary nebula. These are some of the most beautiful objects in the universe, glowing clouds of ionized gas in spectacular colors, with the dying star's core at the center. That core, now exposed, is called a white dwarf. It's incredibly dense, packing roughly the mass of our sun into an object about the size of Earth. A teaspoon of white dwarf material would weigh about 15 tons. White dwarfs don't die explosively. They just slowly cool down over trillions of years, eventually becoming black dwarfs, though the universe isn't old enough yet for any black dwarfs to exist. This type of death won't kill us because it happens slowly over thousands of years, giving any civilization plenty of time to evacuate or adapt. Now let's talk about the deaths that could kill us, starting with novae. A nova occurs in binary star systems where a white dwarf is stealing material from a companion star. As hydrogen accumulates on the white dwarf's surface, it gets compressed and heated by the white dwarf's intense gravity. Eventually, conditions become right for runaway thermonuclear fusion, and the accumulated hydrogen explodes in a tremendous blast. The star suddenly brightens by tens of thousands of times, hence the name nova, which means new star. Ancient astronomers thought they were seeing new stars appear in the sky. But here's the thing about novae: they're not actually deadly to us. The explosion happens on the white dwarf's surface and doesn't destroy the star. The system can repeat this process multiple times. Novae occur relatively frequently in our galaxy, maybe 25 to 50 per year, and we're in no danger from any of them because they're just not powerful enough to threaten life at interstellar distances. But when you add more mass to a white dwarf, something terrifying happens. If a white dwarf in a binary system continues accumulating matter from its companion and reaches about 1.4 times the mass of our sun, called the Chandrasekhar limit, it can no longer support itself against gravity. The entire white dwarf undergoes catastrophic thermonuclear detonation in what we call a type Ia supernova. This is different from a nova because the entire star explodes and is completely destroyed in seconds. Type Ia supernovae are incredibly luminous, briefly outshining entire galaxies. They release roughly 10 billion times the energy output of our sun and remain visible for weeks or months. These explosions are so consistent in their brightness that astronomers use them as standard candles to measure cosmic distances. Could a type Ia supernova kill us? Absolutely, if one occurred close enough. Within about 50 light years, the radiation in cosmic rays could strip away Earth's ozone layer, exposing the surface to deadly ultraviolet radiation and causing mass extinctions. Fortunately, there are no known white dwarf binary systems that close to us approaching the Chandrasekhar limit. Now we enter the realm of core-collapse supernovae, and this is where stellar death becomes truly apocalyptic. When massive stars, those with at least 8 times the mass of our sun, reach the end of their lives, they die very differently from stars like our sun. These massive stars fuse progressively heavier elements in their cores throughout their lives, creating layers like an onion. Hydrogen fuses to helium, helium to carbon and oxygen, carbon to neon and magnesium, and so on, all the way up to iron. But here's the problem. Fusing iron doesn't release energy, it consumes energy. So when the core becomes iron, fusion stops. Without the outward pressure from fusion to counteract gravity, the core collapses catastrophically in less than a second. The core collapse is one of the fastest, most violent events in physics. The iron core, roughly the size of Earth, collapses to a neutron star about 20 kilometers across in less than a second. Electrons are forced into protons, creating neutrons and releasing a flood of neutrinos. The infalling outer layers of the star crash into the suddenly rigid neutron star core and bounce back, creating a shockwave that tears the star apart. This is a core collapse supernova, specifically Type 2, and it's roughly 10 times more powerful than a Type Ia supernova. The explosion releases more energy in a few seconds than our Sun will produce in its entire 10 billion-year lifetime. Core collapse supernovae create and distribute all the heavy elements in the universe. Every atom of carbon, oxygen, iron, gold, and uranium in your body was created either in the core of a massive star or during its supernova explosion. We are literally made of stardust from ancient supernova explosions. But could one kill us? Absolutely. A core collapse supernova within 25 to 50 light years could potentially cause a mass extinction on Earth. The good news is there are no stars massive enough and close enough to pose an immediate threat. Betelgeuse, the red supergiant in Orion, will eventually go supernova, but at about 650 light years away, it's far enough that it will just be a spectacular light show, potentially as bright as the full moon for several weeks. But some stars don't stop at neutron stars. If the collapsing core is massive enough, nothing can stop the collapse, and it forms a black hole. When this happens, the supernova can fail, with the outer layers falling back into the newly formed black hole, creating a relatively dim explosion, or it can create something far more terrifying. Enter the hypernova. Hypernovas, also called supernovae, are the most energetic stellar explosions involving normal matter. They're roughly 100 times more powerful than regular core collapse supernovae. Hypernovas occur when extremely massive stars, possibly 25 to 50 times the mass of our Sun or more, collapse directly to black holes while still rotating rapidly. The rapid rotation channels some of the explosion's energy into narrow, incredibly powerful jets that punch through the star's poles at nearly the speed of light. These jets carry an enormous amount of energy and can extend for light years into space. If you're in the path of one of these jets, you're in serious trouble. Hypernovas are thought to be the source of long-duration gamma-ray bursts, and this brings us to the most dangerous stellar death phenomenon in the universe, gamma-ray bursts. Gamma-ray bursts, or GRBs, are the most energetic events in the universe since the Big Bang. For a few seconds to a few minutes, a gamma-ray burst can outshine every other gamma-ray source in the observable universe combined. A typical long-duration GRB releases more energy in 10 seconds than our Sun will emit in its entire lifetime. If you converted the mass of our Sun directly into pure energy via Einstein's famous equation, that's roughly equivalent to the energy in a powerful gamma-ray burst. There are two types of gamma-ray bursts. Short-duration GRBs, lasting less than 2 seconds, are likely caused by collisions between neutron stars or a neutron star and a black hole. These are catastrophically violent events but relatively rare. Long-duration GRBs, lasting more than 2 seconds and sometimes for several minutes, are associated with hypernovae and the deaths of the most massive stars. When these stars collapse to form black holes, if they're rotating rapidly, they can launch twin jets of matter and energy from their poles at 99.9% the speed of light. These jets are tightly focused, like cosmic death rays, with opening angles of just a few degrees. Here's what makes GRBs absolutely terrifying. Their focused nature means all that energy is concentrated into a narrow beam. If Earth were in the direct path of a gamma-ray burst from even thousands of light years away, it could be catastrophic. The gamma radiation would hit our upper atmosphere, triggering chemical reactions that would destroy the ozone layer within seconds. The burst would also create nitrogen oxides that would further deplete the ozone and create a brownish haze in our atmosphere, blocking sunlight and cooling the planet. The loss of the ozone layer would expose the surface to lethal doses of ultraviolet radiation from the sun, killing phytoplankton in the oceans and destroying the base of the food chain. This could trigger a mass extinction event. Scientists have speculated that the Ordovician mass extinction roughly 450 million years ago, which killed about 85% of marine species, might have been caused by a gamma-ray burst striking Earth. The evidence is circumstantial but intriguing. The extinction pattern matches what we'd expect from ozone depletion and a climate cooling event. Could a gamma-ray burst hit us in the future? It's possible but not likely in the near term. Gamma-ray bursts are rare, occurring perhaps once per galaxy every few 100,000 to million years. Moreover, for a GRB to affect Earth, it would need to be both nearby within a few thousand light years and pointed directly at us. The jets are so narrowly focused that even a slight misalignment would cause the burst to miss us entirely. Astronomers have identified a few stars in our galaxy that could potentially produce gamma-ray bursts when they die. Wolf-Rayet stars, which are extremely massive and nearing the ends of their lives, are candidates. WR104, located about 8,000 light-years away, has been called the potential GRB threat, but recent observations suggest its rotational axis isn't pointed at Earth, so we're probably safe. Even Eta Carinae, one of the most massive and unstable stars we know, is probably not oriented to threaten us with its jets if and when it explodes. Let's talk about what would actually happen if a gamma-ray burst hit Earth. The initial burst of gamma rays would arrive traveling at the speed of light, giving us no warning. The atmosphere would absorb most of the gamma rays, preventing them from reaching the surface directly, but this absorption would heat the upper atmosphere dramatically and trigger the chemical reactions I mentioned earlier. Within hours, the ozone layer would be largely destroyed. Over the following days and weeks, harmful UV radiation levels would increase dramatically. Plants would experience something like a sunburn, with photosynthesis disrupted. Phytoplankton in the oceans would die off rapidly. The cooling effect from the nitrogen oxide haze would reduce global temperatures, potentially triggering an ice age. Food chains would collapse from the bottom up. It would be an extinction event to rival the asteroid impact that killed the dinosaurs. But there's an even more exotic and potentially more dangerous stellar death: the birth of a magnetar. Magnetars are a special type of neutron star with magnetic fields trillions of times stronger than Earth's. They're so powerful that the magnetic field alone distorts the atoms in the neutron star's crust, creating starquakes that release enormous bursts of X-rays and gamma rays. A magnetar within 10 light-years of Earth experiencing a giant flare could potentially damage our ozone layer and affect our magnetosphere. In 2004, a magnetar called SGR 1806-20, located about 50,000 light-years away on the other side of our galaxy, released a giant flare that briefly affected Earth's ionosphere despite the enormous distance. It was the brightest event ever recorded from beyond our solar system. If that flare had occurred from a magnetar just 10 light-years away, it could have caused significant damage to our atmosphere and potentially triggered a mass extinction. Now, which of these stellar deaths poses the greatest actual threat to us? Let's assess the real dangers. Planetary nebulae and white dwarf formation won't affect us because our sun won't become a red giant for 5 billion years, and even when it does, the process is slow. We'd have millions of years to see it coming. Novae are too weak to threaten us at interstellar distances. Type Ia supernovae could be dangerous within about 50 light-years, but there are no known candidates near us. Core collapse supernovae could threaten us within 25 to 50 light-years. Betelgeuse will eventually explode, but it's too far away to harm us. Just give us a spectacular show. The real threats are hypernovae and gamma-ray bursts, but only if they're pointed at us, which is statistically unlikely. The most realistic threat might actually be a nearby supernova within 30 light-years that we haven't identified yet, possibly a massive star hidden by dust or a white dwarf binary system we haven't discovered. The cosmic threat is real, but not imminent. The universe is dangerous on cosmic timescales, but humanity has bigger and more immediate problems to solve right here on Earth. However, there's something profound about studying stellar death. It reminds us that we live in a universe of unimaginable violence and energy, where stars billions of times more massive than all of humanity's combined existence die in explosions, so powerful they forge the very atoms that make up our bodies. Every element heavier than helium in your body came from a dying star. You are the universe experiencing itself, made from the ashes of stellar apocalypses that occurred billions of years ago. Those same forces that could destroy us are also the forces that created us. We exist in a narrow window of cosmic time and space where conditions are stable enough for life to flourish, but violent enough to create the heavy elements life requires. The study of stellar death isn't just about understanding how stars die. It's about understanding our origins, our place in the cosmos, and the fundamental forces that govern reality itself. Every type of stellar death teaches us something different about physics, from quantum mechanics in white dwarfs to general relativity in black holes, from nuclear fusion in supernovae to particle physics in neutron stars. By studying how stars die, we learn how galaxies evolve, how elements are distributed through space, how planets form, and ultimately how life becomes possible. So while a gamma ray burst or nearby supernova could theoretically end life on Earth, the probability of such an event occurring in humanity's future is extremely low. We have far more immediate existential threats to worry about, from climate change to nuclear war to asteroid impacts. But the fact that we can even contemplate these cosmic dangers, that we can observe dying stars billions of light years away and understand the physics governing their destruction, that we can calculate the odds and assess the threats, is itself a testament to the power of human curiosity and intelligence. We are a species aware of our cosmic fragility, and that awareness might be our greatest strength. The universe may be violent and dangerous, but we're here, we're observing it, we're learning from it, and we're working to ensure our survival against whatever cosmic threats might come our way.